So today we're going to talk about reasoning in LLMs, largely in the context of natural language. Okay. Uh, so reasoning is hot and is becoming even more important and trendy. This year's ACL 2024 keynote was one of the keynotes was about can LLMs reason and plan. If you look at all the recent publications, if you look at this year's EMNLP or ACL or NSCL, NACL, NSCL, or NeurIPS, ICML, ICLR, you'll see that every year from starting from 2022 onwards, a lot of papers on reasoning. A lot actually, unprecedentedly lot, and people claiming. So there are two types of research that's going on. One is the claim that LLMs can do reason and look at this and look at that, and the other kind of research that's going on is that no, they are not really reasoning, and this is the reasons why they are not reasoning. Okay, so we'll look into both of that, but before that, we want to understand a little bit about what exactly is reason. Okay, so drawing from let's say in philosophy or in logics, in mathematical logics, the one description of reasoning is that it has to infer something that's new. You know, so a new assertion, where an assertion can be a specific fact about a certain status of an object or an entity. So infer a new assertion from a set of assertions, right? So that can be one description. Another description can be that if not an assertion, you can also infer an action from goals and knowledge. So let's say that you have this is more to do with planning. So let's say you have a goal, you have a final goal, and you have some domain knowledge. So can you figure out a particular sequence of actions or a policy in the parlance of reinforcement learning? And if you are able to figure out an optimal a series of action or sequence of action, then you are able to do reasoning, right? In contrast, what isn't reasoning? So if you are just directly experiencing something and just stating that out through direct experience, then that is not reasoning. So which means that if you already have access to a particular assertion which is there in your database and you're just retrieving it, then that's not reasoning. Okay, so reasoning has to be something that is innate, that is not explicit, and you are deducing it or inducing it in some particular reasoning way. We are going to look into that, and finally stating that, right? So that would be reasoning. In NLP, it has to be more than understanding. So it has to be more than NLU, natural language understanding. So something related to slow thinking, which means you pause, you think through the solution, and then you try to finally come up with the answer, right? So as an example, let's say multi-hop question answering. So essentially, before what you do is, what the model does is, the model stops or restrains itself from straight away giving an answer. So instead of straight away giving an answer to a question, the model breaks the question and gives some intermediate answers, and then finally arrives to the final answer, right? So that's sort of mimicking what we call as slow thinking. Also, common sense reasoning would be another kind of reasoning in NLP. What is not reasoning in the context of NLP would be memorize and look up or retrieve what I just said, or match information. Like as an example, text summarization is not should not be considered as reasoning. Style transfer should not be considered as reasoning, right? So if I have to we have to combine these two ideas, one from philosophy and one from NLP, and then perhaps arguably, and again I'm stressing on the word arguably, uh, one can say that reasoning is a dynamic process to integrate multiple knowledge, and by multiple knowledge, what we mean is knowledge which are external, which can be found on the web or some other kind of database or a search engine, to get new conclusions rather than direct recourse to memorized or provided first-hand information, right? So that is important. So if you are just fetching a particular assertion, that's not reasoning. But if you're fetching certain kind of premises, and then based on the premises you're deducing or inferring something, then that would be considered as reasoning. So the key point to note over here is that new assertion, as in philosophy, versus slow thinking, right? So that's the key thing. And if any of you have not read this particular book by Dan Kahneman, please grab hold of this one from the library, and it's a really good book. It's on this in a specific thing about what's the two types of thinking. One is fast thinking and one is slow thinking. So you'll get to understand some good, deal of slow thinking from a cognitive science point of view. Uh, Now, there are three types of conclusion that one can draw using a reasoning process. One is basically new assertion. As an example, if you are given a premise, by premise it means known, something that is a known statement which is true, which you assume to be true. And let's say that one of the premises cat is animal, the second premise is animal can breathe. And therefore, let's say that you conclude that cat can breathe. So that would be reasoning. Why? Because cat can breathe is not an assertion that was explicitly in the database or in the knowledge base, right? That's something that you inferred. So that would be one kind of conclusion. Another kind of conclusion is where you actually conclude a particular event that was not there, but you can infer that. As an example, let's say there is an already given event which you use like a premise, such as John was shot, and then let's say there's another event, there are people around, and then there's a third event, third information rather, doctor can save lives. So, and let's say that the system infers John will be sent to a doctor. So that inference is an inference of an event, of a new event, which you infer from already existing common sense and domain information and the existing event. The third kind of conclusion can be when you actually come up with a new action or a new set of actions or a new plan. As an example, if you have one premise, Mary is in the living room. By the way, there's a typo in the paper. I mean, it should be Mary, not Mary. But yeah, so Mary is in the living room. Mary feels it is hot, and let's say remote control for air conditioner is in the bedroom, and the system comes up with this plan: go to the room, take the remote control, come back, and turn on the air conditioning. So that would be another kind of conclusion that one derives from a reasoning process, right? So what does not count as reasoning? So this is a good way of sort of trying to understand, and this was kind of like very recently proposed by this group of people from the Chinese University of Hong Kong and Hampstead University in this really wonderful survey paper that came out very recently. And it's an interesting way of looking at it, trying to understand what does not sort of count as reasoning. And one example, what they said is that entity linking, like as an example, if you have been given an input, they performed Kashmir. Kashmir is a song, by the way, and they performed Kashmir written by Page and Plant. And if the output example is Kashmir should be mapped to Kashmir, the song, Page should be mapped or linked to Jimmy Page, and Plant should be mapped to Robert Plant. this mapping is should not be considered, according to them, should not be considered as reasoning. And the reason being that, is just aligning known entities without producing new assertions. So it's not that it's actually coming up with new information. It's just like mapping two known entities together, right? So that's why it's not a reasoning according to them. Another example would be, let's say that you are given these three key phrases or keywords: dog, frisbee, catch, and throw, and you're asked to describe a daily scenario using these concepts. And let's say that the model comes up with this sentence saying a dog leaps to catch a thrown frisbee, and that's also not reasoning. The reason being that it's a new text, but it's neither claim true assertions or events or generate actions. So in other words, it is what it is not claiming. The system is not claiming that, oh, this is a true statement. All the system is doing is that, oh, this is a sentence. I've generated a sentence. Now don't ask me whether this sentence is a true sentence or a false sentence, because that's a guarantee that I won't give you, because I have not deduced it. So this sentence has not come through a series of deduction or logical deduction or logical induction, and that's why I can't guarantee you that this statement will be true. All I can say that this is a viable statement. This is a statement that has some meaning, but whether this is true, I don't guarantee, right? So that's why it's not reasoning. So generating sentences just in the sake for the sake of generating sentences is not really reasoning, according to this survey. And the third example would be open domain question answering. So, like as an example, what color was John Wilkes Booth's hair? And let's say you are given a context, and the context is he stood 5 feet 8 inches tall, had jet black hair, and let's say that the answer is jet black is the hair color. Now, why is this not reasoning? Because the answer is already in the context provided. You are just extracting the answer out of the context. So if you're just extracting the answer out of the context and not creating any new assertion, then it should not be considered as reasoning, right? So moral of the story is that not every NLP or NLU task should be considered as reasoning, right? So whatever your LLMs are doing, not everything that your LLMs are doing should be considered as reasoning. And this is for you to think about, that whether entity linking 2 should be considered as reasoning or not. According to the survey, it's not. But, well, one can also argue that the link was missing. It was not known that Kashmir is actually Kashmir the song and Page is actually Jimmy Page. So since that information was missing, and now since you have deduced or sort of like come up with that assertion, so maybe entity linking is reasoning, and you can always argue for it as well. So I'm just playing the devil's advocate over here. Okay, so very quickly, so to sum it up, you will be, for a reasoning to happen, you have to have some propositions, which are just statements that are supposed to be true, and you have some premises, which is statements that you use for the inference procedure. So not all of the propositions you will be using for your reasoning. So you will be using some of the propositions for your reasoning, and those propositions that you use for your reasoning, they are called premise. And then finally you can come up with some intermediate conclusion, and then build over it, build on top of it, and to come up with the final conclusion. So an example, again, this is another example where they try to clear about what is not a reasoning. As an example, all human will die, unless the model says death is waiting for every human. So that's just paraphrasing, right? So that's not some new assertion that you got out of it, right? So that's but if I say that there is another statement or and which you are using as a premise, let's say Aristotle is a human, and then if you say Aristotle will die one day, that is reasoning, because that assertion, Aristotle will die one day, was not there before, right? It's not some paraphrasing or rephrasing an information that was already there. Again, Aristotle was a Greek born in 384 BC. Uh, from there, if you just say Aristotle was a Greek, it's just shortening the statement. It's not a new statement that you came up with, right? So that's not reasoning. So three types of sort of neat, I like to call them neat reasoning. One is deduction, which you have always done in mathematics. Most of the proofs that you do in mathematics is deductive in nature. So as an example, Aristotle is a human, and you have a rule: all humans will die. It's a general rule. And then let's say Aristotle will die. So from fact one, and you add the rule and you get fact 2, so that's deduction, right? Induction would be where you actually start with specific instances as truth, and then you try to generalize on top of that. And a neat way of doing that is what you would do in mathematics through inductive reasoning or proof by induction, right? So that's what. But even if you're not doing something as neat as proof by induction, you may also try to probabilistically make a generalized statement, using some sort of uncertainty involved, but you can make a generalized statement using induction, like, with, let's say, with 80% probability, if I combine fact 1 and fact 2, which means if I combine Aristotle is a human, Aristotle will die, then with 80% probability it would mean that all humans will die, let's say, or 70% probability it means that all humans will die. So that would be induction. Abduction is a bit different, and abduction is more about, if I give you the fact, let's say fact 2, that Aristotle will die, then what is the most plausible explanation for that fact to be true? So if you assume that Aristotle will die, then what is the most plausible reason or explanation for that? And if you come up to that thing, that okay, the most plausible reason being that Aristotle is a human and the fact that all humans will die, that is the explanation that Aristotle will die. So essentially, abductive inference is to infer probable knowledge as the best explanation or the best cause of something that you are already observing or seeing. So there's a fourth kind as well, and it's called defeasible reasoning. It's a particular kind of non-monotonic reasoning, and let me just give you an example to make you understand what it means. So let's say birds can fly, right? So that's a statement that's given. It's a very, very common example. Let's say Tweety is a bird, which means you would now deduce that Tweety can fly. So that's deduction. Then you came to realize that Tweety is a penguin and penguins don't fly. So then you retract, or you defeat your previous quote unquote, defeat your previous conclusion that Tweety can fly, and you modify it, and you say that therefore Tweety is sad since she can fly, right? And this goes through over time, which means you keep on seeing new information, and you modify your previous conclusions. It doesn't happen in classical deductive reasoning, where once you have already established a conclusion, you stick to that conclusion. You think that the conclusion is always going to be valid, but that's not true for defeasible reasoning. So the difference being that deductive inference will always be valid, while this would be probably valid, sort of. So the inference relation being that you're always going to say, whatever inferencing you're doing, You're basically finally supporting the final conclusion, while over here you are just strengthening, or sometimes even weakening, or sometimes even rebutting or retracting your previous conclusion. So that can happen. An important aspect of deductive inference is that you cannot do deductive inference unless you have a bounded set of axioms, or what we call as domain knowledge, right? So unless you have that bounded set of premises or axioms, you can't do deductive inference. Whereas the interesting thing about diffeasible inference is that you can keep you are flexible, which means that even in the future you allow new information to sort of unsettle your previous conclusions, and you're willing to be open enough to new information and to change your opinions. So that's what unbounded would mean. Okay, so now comes the interesting thing. I mean, this what we call as natural language inferencing, NLI, sometimes also called as RTE, or basically identifying textual entailment. So this is a very old standard NLP task that has been even before we were all, going around and talking so much about LLMs and reasoning and so on and so forth. So let's have a closer look at whether NLI is reasoning or not. Right. So as an example, let's say the paraphrase case, which is two doctors perform surgery on patient, and one NLI hypothesis would be doctors are performing surgery, right? But that's not reasoning. That's just paraphrasing. That's not a new assertion. That's not a new statement that you got. It's an entailment in some sense, but the entailment doesn't lead to any new assertion. So that's why it can't be considered as reasoning. Let's say the second situation, where you have two women are embracing while holding to-go packages, let's say, and you come to this conclusion that two women are holding packages. Also, two women are embracing. Now, that again is not, I mean, that's an entailment, definitely, but that again is not reasoning, because that's not adding any new assertion to the knowledge base. Reasoning would be like a soccer game with multiple males playing. Let's say soccer is a sport, and that's an implicit knowledge that is there. And some men are playing a sport. Now, when you say that some men are playing a sport, and where you add up these two assertions that soccer is a sport and a soccer game with multiple males playing entails this, then you can say that, yeah, this third case is actually a case of reasoning. So moral of the story is, not all NLI problems can be considered as reasoning. Only a few of those NLI cases can be considered a reasoning, right? So that's the thing. So again, so just to remind you that it's integrating multiple knowledge to get new conclusions, rather than direct recourse to memorized or provided first-hand information, right? Okay, there are some special cases of all these four kinds. What are the four kinds? Deductive, inductive, abductive, and defeasible. So there are four special kinds. There are a few special cases of these four kinds. Arithmetic reasoning being one of them, and they are mostly deductive. Statistical inference is mostly inductive in nature. Common sense reasoning is mostly abductive, where you are mostly interested in the explanation or the cause of something. Let's say that if one fine morning you see the grass wet, so you probably your explanation might be that, oh, there must have been rain yesterday night, and that's why the grass is laying. So that's abductive reasoning. And many times it's also inductive reasoning as well in common sense reasoning. And then there is spatial reasoning, sorry for the typo, is mostly deductive in nature, and but at the same time there's a lot of inductive spatial reasoning as well. And then there is temporal reasoning, which is deductive, inductive, as well as you see a lot of abductive reasoning as well. Temporal reasoning would be, let's say, which event occurred first, which event occurred next, which event overlaps which two events, and so on and so forth. Those are sort of reasoning. uh, Spatial reasoning is pretty much the same sort of similar thing, but at a locational, a geolocational frame level. So whether two events are occurring at the same place or occurring side by side geolocationally, and so on. Um, okay. Uh, just a closer look at statistical inference, and this is not something that a lot of people talk about these days, but I'm a big fan of this guy. His name is Julia Pearl. I am very sorry that I did not put his name over there. uh, Turing awardee, and one of the proponents of causal reasoning. And he came up with this framework, and he said that, okay, what's really going on, if you have to understand reasoning, is that there are three ladders, or three sort of levels of reasoning. And what we are currently doing with LLMs or machine learning models is the very first level, the very basic level, and that's association. So what is association is basically as simple as trying to understand the conditional probability, and you have already understood that how LLMs work or language model work is basically conditional association, is where you're trying to understand that, okay, if you have already observed a random variable to be X, then what is the probability that the outcome variable will be Y, right? And is as simple as that, but it does not tell you anything more than association. So it does not tell you anything about the causality or anything else as such. So that's pretty much what ML does. uh, then you have a little bit advanced, more higher up, where you are saying that, what if I intervene, and what if I change the random variables, the input random variables input value to X, and then after doing that, if I see this even Z, then what is the probability that Y will happen as an outcome, as a follow-up? So if I intervene, let's say that the random variable capital X was something else, and I intervened and I changed that to small x, and because of that I saw this new event happening, which is Z. Now what is the probability that as a follow-up Y will happen, right? So that's and I'm not going into the details of that, but if you're interested, you can see there's something called do calculus and so on and so forth. So it's more, and this is what AI planners do, where they always try to figure out whether this is a viable action, and sometimes they backtrack, if they don't see certain things to be a viable action down the line. They backtrack and then again try to move into a different, take a different plan, and in order to reach the final goal. So that's the intervention part. So you can only get to know it when you do it. You won't get to, there's no training data as such that can help you to decipher it. Despite all the training data, you have to do the thing in order to really see that Z actually happened, right? And then you can talk about Y. The third thing is extremely important, and that's where the final level is. It's called counterfactuals. And what it means is that if I imagine that, let's say capital X, and let's say that if I imagine that capital X, the random variable, takes up the value of X prime. That's not what happened, but I'm just imagining that, what if X becomes X prime, and what if as a result the outcome Y becomes Y prime, Okay, and now if that is so, then if I change x from x prime to x, small x, then what is the probability that y will change from y prime to y? Capital Y will change from y prime to y. So the idea is that if capital Y was y prime, and if capital X was x prime, or if I imagine that to be like that, and then if I imagine that x prime becomes x, then what is the probability that y prime becomes y? So and usually that's dealt with some sort of structured causal models, and there are different types of structural causal models. I'm not going to go into that, but if you're interested to get a easy reading, then this particular book, The Book of Why, by Julia Pearl and Dan McKenzie, is really interesting. You should just grab it and just go through some part of it, and it's really interesting. Okay, so now the techniques, right? So we talked about what is reasoning, the varieties of reasoning. So now the techniques, the contenders. So natural language reasoning has three different, very broadly speaking, three different techniques. One is end-to-end reasoning, which you most of the cases which you see, much of the literature is about end-to-end reasoning. I'll give you a very easy example of what that is, and how that differs from the other category, which is forward reasoning. And then there's this third category, which is backward reasoning. Right. So end-to-end reasoning, usually you'll see that it's like a black box. You don't really have a stepwise procedure as to why certain things happen and why you concluded certain things. So that intermediate thought process, or thinking it loud, is not there in end-to-end reasoning. Right. Forward reasoning is, it's more interpretable, but the biggest problem is that, as you will see, the search space increases, because you have to open up all the possibilities and then search through all the possibilities, and then in order to give that interpretation, which means in order to show the entire path of to leading to the final conclusion, you have to open up or unfold all the paths, that and then show, and then you negate, saying that, oh, this won't lead to the final conclusion, this won't lead to the final conclusion, and then you narrow down to one specific path, and then you explain that path. But in order to do that, elimination, you have to unfold that entire set of possibilities, and then, so that's why it's computationally quite expensive. And backward reasoning, one major problem is that you go backwards. It's just the opposite of forward reasoning. So you start from the end, and then you come to the beginning, sort of. And I'll show you an example. And because you always start from the end, it becomes too tied up to the goal, to that one particular goal, which means that the same sort of reasoning you cannot generalize for similar kind of goals, which means you take one goal and you come backward, and while you come backward to you are able to explain sort of why how you reach that goal. But it's very difficult to generalize this sort of reasoning process. Okay, so how they differ. So let's say that I ask this question: who is older, Obama or Michelle? And then the model straight away gives me this answer. The answer is Obama. That would be end to end, which means the model did not tell me several things, which probably the model used as a part of the latent information that the model has already learned or been trained on. As an example, Obama was born in 1961, Michelle was born in 1964. 1961 is early than 1964, but it's all hidden. So it's all hidden from us, from the user. So that's why all we get to know is that we give this input question and we get the output, and this would be like an end-to-end, and we train such a model. Let's say that we are trying to train such a model, a question answering system, and we are just trying to figure out a function, which is this hidden function, and we just takes this as an input and maps this to the answer. Now, how that really works, exactly what is the ingredient, how the ingredients are getting combined, we have no clue. We can't interpret that. That would be end to end, right? And then you have the forward chain, or the forward reasoning. So again, the same question: who is older, Obama or Michelle? So what you do is you expand the possibilities, and you say that, okay, all right, so one important thing is that I first need to answer the first question, which is the first part of the question, which is that the age of Obama. So let me answer that. So Obama born in 1961. I'm going to answer the next part of the question, which is the birth date of Michelle. And I said that, okay, I got the answer. Michelle born in 1964. I combine these two, and I then say that Obama was older than Michelle. And then finally, I give the answer. The answer is Obama. And this is all shown to the user, which means this is not hidden from the user. So you are actually step by step working out your thought, kind of very similar to chain of thought reasoning. I'll show you one paper which actually does this sort of thing. The very first paper on sort of one of the very first papers on chain of thought by Google Brain. So this is forward reasoning. Backward reasoning would be just the opposite, where what you do is you take a question, and this is a particular kind of backward reasoning which involves breaking the question or decomposing the question. So you say, okay, so who is older, Obama or Michelle? And you break it up into two further questions. When was Obama born? When was Michelle born? So you are actually breaking up into further sub-queries or sub-questions, explicit questions, which you did not do in forward. There was no explicit sub-questions that was generated. And then you answer those sub-questions, 1961, 1964, and then you again form a new question. Which one is earlier, 1961 or 1964? And you again answer. So it's almost like a soliloquy. It's almost like a monologue, and you are asking yourself some questions and you're answering, back, sort of. So which one is earlier, 1961 or 1964? And you answer yourself 1961, and therefore you say that the answer is Obama. Okay, so note the difference between forward and backward. So in forward, you don't form intermediate questions and then answer back that question and then move forward. That's not how we work. Okay, one specific example of forward reasoning is the chain of thought prompting. So standard prompting would be, as an example, you ask this question: Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And let's say that you give an example in the prompt, which is a demonstration, and you give one example. Let's say this is a case of one shot. So in the case of one shot, you give the example, answer is 11. And then you ask this question, the query: the cafeteria has 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And let's say that the model outputs, and this is what they saw, that the model actually gave the wrong answer, and the wrong answer in this case is 27. But the moment they did it through a chain of thought sort of a prompting, where they not only just in the example, they did not just give the answer, but they also gave that forward process, so that graph, the forward graph, they actually put that in as a part of the prompt. As in the case of Roger started with 5 balls, 2 cans of 3 balls, each in 6 tennis balls. 5 plus 6 is equals to 11. The answer is 11, right? So that's how they gave that answer. They gave that graph sort of as a part of the prompt. And then they asked the next question, and the model started following that sort of a graph procedure as the example and gave the right answer. and they try to experiment that. And this is a new RIPS 2022 paper by Google Brain, and they try to explain, experiment that with GPT-3 175 billion and Palm 540 billion, and they looked at Palm 540 billion is lot bigger, and they looked into the without the, I mean, with the standard prompting, just normal plain simple vanilla standard prompting, and then they did the chain of thought. The chain of thought is in red, the standard prompting is in yellow, and you see this big bump in terms of the math word problems, which is there in the GSM benchmark data set. And the solving rate improves significantly, as you can see. So 57 correct answers out of 100 questions. So every time it asks 100 questions. So these are math problems, arithmetic, plain simple arithmetic problems, and the example that you see over here. Okay, so now an example of backward reasoning, or backward chaining. So this is a paper, it talks about this model called Taylor. This is a paper by AI2, Allen Institute, published in EMLP 2022. And again, what they do was that, let's say that this is the question: do plants require CO2 to make their own food? They break it up into two possible subqueries. Plants require, hypothesis rather, plant require CO2 to make their own food. Plants do not require CO2 to make their own food. And from there, they start generating entailments. And one example entailment is something like this, where they say that let's say that paperclip conducts electricity, and which is further broken down into two hypotheses. A paperclip is made of metal, and metals conduct electricity. And again, paperclip is made of metal is again then further broken down into smaller parts, or which are again forms as the premise of the which is a paperclip is made of steel, and steel is a metal, right? And so on and so forth, right? So basically, what it does is that it takes a particular a particular premise, which is paperclip conducts electricity, and then it goes downwards. It generates the smaller premises from the bigger premise. So it's sort of like top down, and it generates downwards sort of. So these two green nodes that you can see. So if I break down in those two green nodes are the smaller premises, right? The shorter premises. And if I see that this shorter premises, the probability is one is of 0.9 and one has 0.8, so the joint probability would become 0.72. So I revise 0.75 and I overwrite 0.75 to make it 0.72, and then again I break it down one step further into the next two. So it's like top down, the next two premises, the sub premises sort of. And if and again I try to understand what is the probability of the sub premises, and if it turns out to be 0.6 and 0.8, so my 0.9 is then revised to 0.29, and then 0.29 and 0.28 will again get revised, and 0.72 will get revised accordingly, and so on and so forth. And finally, I will have the final sort of a proof with certain score or certain probability of that proof, and let's say that probability turns out to be 0.81. So that's how I keep updating, and while generating the proof, I also generate all the sub premises, and the sub premises will constitute my explanation. In other words, I say that the topmost node or the topmost premise is true because the next two nodes are true, because the next three nodes are true, the child nodes are true, because their children are true with certain probability. So that's how I sort of look into this entire thing, and I cross out those sort of twigs which are very low probability, and I only take those ones which have higher probability. And that's how I say that, okay, plants require CO2 to make their own food, which would mean that plants require CO2 for photosynthesis. That's one sub-premise which I found to have a higher probability. The other sub-premise is photosynthesis makes food for the plant, which also has a with higher probability, a sub-premise. And I put them together to finally justify my original hypothesis that plants require CO2 to make their own food. However, the other branch, plants do not require CO2 to make their own food, that automatically got cancelled out because the sub branches or the sub premises could not gather enough probability in terms of how much possibility they have being true. So they could not gather enough probability to push that upwards towards the other node, and that's why that got cancelled out. So that's the idea. Okay, so the results were like, when they just did direct versus when they tried entailer, and they always got a better result on these two data sets, the OBQA data sets and the Quartz data set, in terms of this technique. So how do we know that these LLMs are good at reasoning? So there are standard benchmark tasks or data sets for all these different types of reasoning: classical logical reasoning, natural language inference, multi-hop question answering, common sense reasoning, complex reasoning, and some others. As an example, logical reasoning, you have all these data sets, mostly to do with theorem proving, but some are also to do with inference. And these are mostly synthetic. Synthetic means these are automatically generated through some seed data, because these are just logical statements. So you can actually generate true and false statements using smaller clauses that are either true and false. And one of the most famous, most used ones is Babel 15. But then there's another one called Logic Glue, which is also quite famous in this in this challenge, which is logical reasoning challenge. Then there is a defeasible reasoning task, which is deductive reasoning, but can be defeasible, which means there is a possibility that you backtrack or you retrack or you change your previous conclusion. So there are data sets on that. One is Babel 16, and another quite used data set is DEAR. Then there is defeasible NLI. So these are that sort of data sets. So just to remind you, what is defeasible inferencing? So NLI, again, there are lots. Actually, there are lots. It started with SNLI back then in 2018, and then you now have a lot of different types of. Recently, you have the scientific tail, the science tail, and the science NLI. So these are also very standard data sets that's used for reasoning at the NLI level, or rather entailment level. But entailment, which can be considered as reasoning. As I said, you remember that not all entailments can be considered as reasoning. So multi-hop query, again, basically all these sort of data sets are there. Two very important data set. One is Hotpot QA and one is Music. I give you one example. So the first one on the left is Hotpot QA that came up in EMNLP 2018, and the question data set looks something like this. As an example, Armageddon in retrospect was written by the author who was best known for what 1969 satire novel? And the answer is Slaughterhouse-Five. let's say the question is, and the follow-up question is, who is the author of Armageddon in retrospect? And the first intermediate answer is Kurt Vonnegut. The second question is, what 1969 satire novel was A1 prime, which is the answer, the intermediate answer, the previous answer, best known for? And then you come up with the the final answer, which is Slaughterhouse-Five. Why it is multi-hop? Because as you could see that the question was broken down into two hops. The first hop, which gave you the intermediate answer, and then the next hop. Now the context over here is basically the overall information from where you gather the answer. And but then in contrast, music came up with this idea that no, you should not give the answer in the context, you should hide it from the context, and so that it becomes a more challenging data set to the and these sort of things come up. So as an example in music, so what music is saying is that this so this Kurt Vonnegut, most famous for satirical novels. So the satirical word is already there in the context. So what it is doing, probably it is just extracting that, connecting that with the answer Slaughterhouse-Five, and it's able to, the model is able to do that. So don't do it. So what it is saying is that don't use the word satirical in the context. Take it out and then try to challenge the model. Okay, so then there is common sense reasoning, open book question answering, which is more about what kind of questions. Like this is an example of a what question. So you give some multiple choice options, you give a fact, you give some common knowledge, and then you ask a question. Then there is what if and why questions, a bit more challenging, and this is very popular data set, the swag and the HelloSwag data set. One example of HelloSwag data set I have given you in the inset, where you pose an event and then you ask what if, let's say as an example over here, what if the woman who was outside with a bucket and the dog was running around trying to avoid a bath, and what if she then does this versus C versus D, which one makes more sense? Uh, so so that's sort of the common sense reasoning. And then the how, there is another kind of common sense which is more to do with the physics of the environment, the physics of our environment. So that is the Pika data set. And as an example, this is this was the paper, the Pika paper came up in AAAI 2020. So two separate egg whites from yolk using a water bottle, you should. So if they give two options, A and B, and then you have to choose which one. So they saw that the model was not able to, at that time they saw that the models were not able to do very good over here. And then there are some mixed ones, like CSQA2, and an example of CSQA2 which was published in News 2021 was this sort of an example where you compose an example, multiple examples, and you ask the model to answer, and then you do a offline validation. And then there are other kind of complex reasoning datasets, lots of complex reasoning datasets, and recently some multitask complex reasoning datasets like MMLU and Big Bench. We talked about Big Bench when we discussed scaling laws, if you remember. So they also have come up with their own very challenging datasets. Big Bench and MMLU is considered to be really challenging. Now, the final part, I'm going to try to be as quick as possible. So, is reasoning reasonably reasoning? So this is where kind of like an eye opener sort of that I wanted to give you guys. So one important thing is very recently in ICLR, 2024 this year, this paper was published called the reversal curse. LLMs trained on A is B fails to learn B is A. So as an example, and they did it with this parent-child sort of a relationship. So if they ask this question and they train or they fine-tune the model on like this kind of question, like who is Tom Cruise's mother? And let's say the answer is Tom Cruise's mother is Mary Lee Pfeiffer. And then they ask, after training on or fine-tuning on these sort of questions, then they ask the model the reverse question, like who is Mary Lee Pfeiffer's son? And unfortunately, the models could not answer back. So the models were not able to answer the reverse question, which is basically which leaves us questioning that whether the models actually did reason, or do they really have the reasoning ability at all or not, right? So this was tested on GPT 3.5 Turbo, Llama 7B, Llama 30B, and Llama 65B. Another test that was recently done in a paper published in NACL 2024 by MIT, some bunch of people at MIT and Boston University, is like they created a counterfactual world. Now, this counterfactual world so this is something that is possible. So it's not a very imaginary sort of a counterfactual world, but something that is absolutely possible. And very simple counterfactuals. Like as an example, if I say, what is 2 plus 2? You would say 4, but that is, you assume that the base is 10, right? So what if I change the base to 9? Then what would be 2 plus 2? So as simple as that, right? So what they did was that when they did that, and they saw that the performance drastically dropped, and they tested it on GPT-4. And let's say for arithmetic, you can see the blue is what they usually did, but when that counterfactual tweak, after doing that counterfactual tweak, let's say just base 10 to base 9, it drastically dropped. The accuracy drastically dropped. And the same thing for code execution. Where the array doesn't start from 0, but the array starts from 1, let's say, the array index. So they just changed that, and again, the performance dropped. Basic syntax where subject verb. So English is a SVO language, but what if you change the SVO into some other order, surface order? And can they, again, after doing that, can they detect the subject or the object? And when they did that, they saw that no, they cannot. Most of the time they cannot. Of course, a bit better than arithmetic or code execution, but not but still dropped. Logic also sort of dropped. So essentially that leaves us questioning the ability of the LLMs to reason through counterfactuals, or in other words, do they even have reasoning capability? Because if they did, they should not have been fooled by such very easy counterfactuals. And finally, this is a very interesting problem. This is just recent. So they haven't yet published in a particular place, but it's done by this Lion AI and ULA lab and University of Bristol. And what they did was they just said this, that okay, they asked this question: Alice has n brothers and she also has m sisters. Mind the word she. How many sisters does Alice's brother have? Right. So that's the question that they are asking. And the question would be basically m plus 1, including Alice, because Alice is she, right? So, and then they did all these variations. Basically, the variations is just basically changing the value of n and m. And what they found out, and this was the prompt. So they gave a standard prompt, and then they also gave a thinking, or it's kind of like a chain of thought sort of a prompt as well. Like slow thinking sort of. So before providing answer to this, think carefully and double check the path to the correct solutions for any mistakes. Provide that final answer. And so it's kind of like slow thinking sort of thing. And what happened was, that when they did this experiment, and they did this experiment across almost all the state of the art LLMs, all of them, they did not leave anything, including GPT-4o, the most recent one, GPT-4o Mini, Claude 3 Opus, right? And what they found out was that the response, the correct response rate was not really very good, and it was somewhere around 6, somewhere around 6 in the interval, some interval of 6 out of 10, 6 correct ones for GPT 4o, right? So that's the best one over there. And when they try to go for the variations, which is the AIW plus, they call it, which is all these variations, right? So when they went for the variations, they saw that it dropped like anything. Everybody drastically dropped the correct response rate. And when they tried to look at it in terms of the fluctuations between the correct and the wrong, they saw there's a lot of fluctuations between when they were correct and when they were wrong. So there's not real consistency in terms of how they performed across the different variations, right? So that's also kind of leaves us wondering, whether there is really any reasoning going on or not. And and then the most important thing is that all these models come up at a very uppish level, the red quadrant that I've marked over there. So all these models are doing really good in the MMLU benchmark, and the MMLU is a very, very challenging benchmark, and all these models are doing really good up there. But the moment you do this AIW trick, the Alice in Wonderland trick, they are not able to go beyond 2 out of 10 correct in the x-axis. If you look at it, they are not able to go beyond 2 out of 10. So although they are doing very good in the MMLU task, they are not able to do any better in this very simple task, right? And it's only GPT-4 4o which is doing some where you find something happening at least. So so that's that's the major problem. And these models are actually doing really good even in the GSM task, and the GSM task is a math task, is a math benchmark, and they are doing very good in the math benchmark, and yet they are doing not so good in this very simple task, right? So that's the concern. And but then when they changed she to female, and when they made it explicit that Alice is a female, then suddenly the model started doing better, right? So basically that's quite a thing, but anyway, some key takeaways is that smaller models of course perform worse, that's for sure. Large scale models like GPT-4 and Claude, sometimes they show correct reasoning but still fail in terms of consistency. And then, do we have some more time? Otherwise I won't go into this. But this is something that's talk of the town today. We started out with this talk, which is the planning ability, which is another aspect of reasoning. So just to concentrate on the first three questions. So basically, can LLM come up with valid plans that will achieve a specific goal? So this is the first point. Can LLMs come up with plans that are optimal? So first of all, come up with a plan. Doesn't forget about whether it is optimal or not. That's the first question. The second question is, can you now come up with an optimal plan? Okay, in terms of minimizing the cost, if every action has a cost associated. And then plan verification. If I give an LLM a plan, then can the LLM say that yes, this plan actually leads to the final goal? Which means, will the LLM be able to verify the plan? So basically, this comes from the world of classical planning, and basically something like that. Like you take a robot is there in one room, it picks up the balls from that room and goes to the other room and drops those balls in the other room. Let's say that's the problem, right? So the objects would be two rooms, four balls, two robot arms, then there is a certain predicates like x, which means the relationship between the objects, in terms of their truthness, whether the object is related to the other object or not. Initial state, which means where are all the objects located and how they are located to each other. The goal specification, what is the final goal, and the actions, which is, in this case, what the robots can do and what the robot cannot do. So they use this particular language called PDTL, which is a formal language to describe such problems, planning problems, and it looks something like this. It's very simple, basically. So you say objects, and then in PDDL language you write it like that, and then you have predicates, and in PDDL you write the predicates up like this, and then you have some initial state, and again in PDDL you write these initial states up, and then finally you put and then you have the actions and all of those things, and then you finally put the goal specification, and in PDDL you put the goal and you write the goal like that, and then you give it to a classical planner, and the classical planner just gives plans through it and gives the final set of actions, that the most optimal set of actions. So what these guys did, basically Professor Subbarao's group at ASU and also at Colorado State University, and this came up in NeurIPS 2023. They said that, okay, what we are going to do is we are going to test these language models by giving such PDDLs, but we will translate the PDDLs into natural language, put it into a prompt, and then give the prompt to the LLM and ask the LLM to give me the sequence of actions. As simple as that. I'm just condensing this entire architecture into this. So this would be something like this. So giving, zero shot, one shot, all sorts of PDDL prompts. So a prompt would look something like this. So this is like the PDDL, translated into English, put it inside the prompt, and this is how the prompts will look like, right? So the final question would be, what is the plan to achieve my goal? Just give the actions in the plan. So that would be the final question after you give all this descriptions of the problem. What they found out was that it's quite bad. All these models, including GPT-4o, GPT-4o mini, they were not really very good, even for those plans that are feasible plans. Feasible plans mean plans that are actually correct plans. So when they gave the correct plans, translated that into English and asked for what should be the sequence, they could not get it back. And this was for two types of data sets. One is the blocks world, where all the objects are known, all the states are known, and then there are some mystery block where what they do is that they actually obfuscate certain objects or certain states, kind of like certain intermediary objects or intermediary states. They obfuscate or maybe remove them, or maybe change their name and make the name something else. Because sometimes what happens in LLMs, because it's actually a language model, so when they get to see the name, they start associating the name with the action, and they might start giving the action. So what if you change, let's say, what if I change my name from Sorish to X? But the action will still, the plan will still remain the same if I have to move out of Bharti building, right? So it's like that. So what if I change the name of Bharti to Y, the building to Y? But the plan of action should remain the same. So what if I abstract it out or change it? And what if I do? That's basically the mystery block world. And what happens is that they, if you can look at, if you see this, that they dramatically drop down. Even the best models like GPT-4o is just 28.3% correct, all the time correct when it comes to the planning problem, right? So So this is what happens, when and obviously this was quite intuitive. That as the plant length in the x-axis, as the plant length increases, it becomes more and more complex. So that the accuracy, the correctness goes down, and the blue one is basically O1, GPT O1. That's the blue one. While the at the top, the dotted orange is the classical planner that always does it correct, because there's nothing probabilistic about it. It just plans things out and gets the correct optimal plan out. So basically that's fast downward. That's a classical planner. So how so this is what it does. So basically what these people's point of view is that you should not use LLM as a planner by itself, but you should rather use LLM as generating a set of possible candidate plans, and then you should use a proper planner like a classical planner to figure out which one is the best one out. So the LLMs kind of is like an assistant that helps to narrow down the set of all possible plans, which might be humongous, and then the planner actually comes in and then figures out which one out of those possible generated plans should be a good plan to work on. So the key takeaway is this, that on closer, this is an excerpt from the paper. So on closer examination, many papers claiming LLMs have planning abilities wind up confusing general planning knowledge. Okay, general planning, like wedding plan, let's say. That's a general planning knowledge. A general planning knowledge extracted, and this is the thing. So they just extract the plan out. They are not planning it in the sense of planner. So they are just extracting the plan out from the LLMs, instead of executable plans. So when all we are looking for are abstract plans such as wedding plans with no intention of actually executing them, it is easy to confuse them for complete executable plans. So in other words, when we say executable plans, you're actually in the action of doing it and figuring it out, and there can be obstacles in your environment, and the environment may not be good to you, and you may be blocked, in while taking certain actions. There can be a dead end and you have to come back, you have to backtrack, right? So those are the actual planning in action, sort of. So that's what they are trying to say. So it's not general knowledge that's out there and you're just extracting it out, and it seems apparently that as if these models can plan, but actually no, the plan was already existent as a form of text, and you're just extracting it. It's not the same as planning it out while figuring out how the surrounding is. So my take on that is reasoning even an NLP or an NLU problem? Because you see, NLP means have you been able to process what I just said? If yes, then you are doing NLP. Have you been able to understand what my intent is? So processing doesn't necessarily mean understanding my intention. So you may have a different interpretation, but that's not what I wanted to say, right? So that is NLU. But let's say that I understood you, but I am not able to reason things out after all the knowledge that you gave me. I'm stupid. Well, I did NLU very well. I did NLP very well. But does that mean that I have to do reasoning very well? You got the point. I mean, it's a bit of a philosophical point which I'm trying to throw you and leave this discussion today. So that's the thing. That probably reasoning is something else, and when we try to understand LLMs, LLM is actually at the end of the day an LLM, a language model. So are we asking too much? So that's something that you guys can debate on.